Thank you, Andy. So, the nice thing here is I don't have to motivate why defects are important. So, I guess that's the whole point of this workshop. So, I will skip any kind of motivational introduction. I also managed to catch a cold. I transitioned from Greece to Cambridge directly without going through Paris. So that's really first order, and my voice will be a bit muted, but the room is small enough that it should be okay. So this talk is thanks. So this talk is about super conformal defects. It's not about topological defects. I mean, the equation I will show to you is sort of trivial for topological defects, but it is very universal for any kind of superconformal defect. Now, let's simply to set the notation. So I will have some d-dimensional, can you see? Yeah, some d-dimensional superconformal field theory and a p-dimensional defect. And for the theory to be superconformal, D has to be at most 6. And P has to be less than D. And in principle, P could go all the way down to 0 if you count local operators as defects. But they won't play really a role, much of a role in this equation. So now the plan of the talk is the following. First of all, I will describe the equation and the history of the equation, which is basically relating the one-point function of P mu nu with the two-point function of the displacement operator. So I'll say some words about these things if you don't know them. Then, so that's one. Then two, I'll sketch the proof. Actually, showing the full proof would take me the whole lecture, so I will only sketch it, the basic steps. And then I will talk about two physics applications of this equation. One has to do with holography. This is the only place where I will be talking about quantum gravity, which among various interests is the dearest in my heart. The rest is simply conformal theory. But here I will talk about a question that was already, I think, discussed in Shira's talk on Wednesday, namely, how do you define the tension of the brane which is dual to the conformal defect. And Shira showed you one particular instance where you can relate it to the energy transmission coefficient. What I will show to you here is that in dimensions higher than 2, there are actually two different definitions that are equally legitimate. One is the analog of the ADM mass, and I call it sigma gravitational, and the other we sort of maybe misnamed it sigma inertial because it rings bells, as you will see. A more down-to-earth thing would have been sigma mechanical, and the equation I will show to you basically tells you that the two are equal. And finally, if I have time, I will talk about a very old problem, the radiation reaction. for accelerating charges. So again, I'll show to you what this equation implies in this problem, although this is still open-ended, so we don't fully understand the end of this story. Right, let me mention my collaborators. So these are two papers, one with Zhongwu Chen, my student, Zhongwu Chen, who is finishing this year and goes to the Kavli Institute in Beijing. And this was 2404, 14998. And the other is also with Lorenzo, who is here in the room. And this is the proof. This is the one containing the proof. 13197. But at least for me, Lorenzo comes from a different direction. I will say a few words about it. For me, some of the motivation did come from the work we were doing with Shira, Giuseppe et al., where, you know, the question is, what is the conformal field theory translation of the tension of a string in this case? So in a sense, you know, this part addresses the more general case of arbitrary dimension, but it doesn't quite calculate energy transport as in the seminar of Shira. Okay, so that's the outline. Okay, so before I go on, you know, if you have any questions, don't hesitate, stop me. We don't have to go to the end of the talk if anything interesting comes up. So let me start by describing the equation. Okay, so it's we have conformal field theory in flat space. So this is RD, d-dimensional flat space. We have a defect, which is hyperplanar and static for now. So it's p-dimensional. This includes time. Both p and d for me include the time coordinate, which can be Euclidean or Lorentzian. And now here are the two quantities that are related by this equation. So we take some point x away from the defect, and then the one-point function of the energy momentum tensor is completely fixed by conformal symmetry up to one unknown parameter. So let me write it down as follows. So I will use alpha beta to parameterize the indices along the defect, and ij, Latin indices, to parameterize the transverse directions. And then T alpha j is simply 0 because there is nothing invariant you can write down. T alpha beta, the only invariant thing you can write down is eta alpha beta or delta alpha beta, the invariant metric, over the transverse distance to the power d, right? So this is, well, depends on perspective, it's like this or normal. And this multiplies a coefficient, which is in some conventions d minus p minus 1 over d times the first conformal data, which is in this convention it's called AT. There's some other convention where you call it H, and then it differs by some numerical factor. And finally, Tij is the same AT, and then it has now two tensor structures, xi, xj over x transverse to the power d plus 2 minus p plus 1 over D, delta ij, now this is purely Euclidean, transverse to the defect, over x normal to the power, x transverse to the power D. So, there are tensor structures here, but the key point is that the whole thing depends on a single parameter, AP. Now, this is the parameter number one. Parameter number two is the displacement norm. Now, what is the displacement? Well, it's an operator that does what it says, namely displaces the defect in the transverse direction. And actually, it is defined by the broken conservation law due to broken translation symmetry. The defect breaks the symmetry under transverse translations, and therefore T mu j, the current is not conserved. It has a delta function at the position of the defect times, by definition, the displacement operator, which is an operator that lives on the defect. Okay, it displaces the thing. And now, so this is the displacement operator. And now the second parameter is simply the normalization of the two-point function of the displacement, djy dk of 0. You see from the conservation law, T mu nu, a canonical energy momentum tensor, has dimension d, conformal dimension d. This takes away some number of transverse dimensions, so the dimension of this one is fixed to be p plus 1. Therefore, the power is fixed. It's y to the p plus 2, to p plus 2. But there is a delta jk by rotational symmetry. I'm going to assume always rotational invariance or twisted rotational invariance. And then here is the second parameter, which is called CD. Now, notice that usually two-point functions, we normalize them to 1. But here you cannot do this because of this conservation law, which fixes uniquely the normalization of the displacement in terms of the energy momentum tensor. And therefore, this is also a piece of conformal data. Okay, it's not a trivial thing that you can talk away. Yes? The alpha j, sorry, that's a j. So it's the mixed thing, there's nothing you can write on the other side. Yeah. Okay. Now, these two parameters, here.
P had to be less than E. The stress tensor only can get a one-point function.
Yeah, thanks. I'm going to say this immediately. Indeed. So first of all, let me say that this AT and CD are two universal characteristics of the defect. They enter in all sorts of observables. We'll see some of them. They enter in anomalous dimensions. This one entered in what Shira discussed on Wednesday. When there are conformal anomalies, they control some of the conformal anomalies, as our organizers have shown, Chris, Andy, and maybe Adam also in some of the papers. So they are really a very important part. In a sense, you may say it's the first thing you want to know about the conformal defect. Now, indeed, so they enter in many observables. Now, indeed, as Andy said, CD is not defined, obviously, for p equals to 0, since you only have a point. So there's no way you can construct a two-point function and read the norm of the displacement. So it's not defined for p equals to 0, and on the other hand, AT is not defined for codimension 1. And the reason is that if you check these equations, the right-hand side vanishes automatically when p is d minus 1 for any value of AT. So in a sense, for interfaces, you cannot define AT. And another reason is that T mu nu has no singularity in this case. It goes over smoothly to the displacement operator on the interface. So these things are only defined, therefore, for p bigger than 0 and less than d minus 1. Unitarity forces CD to be positive, and positivity of energy forces with these conventions AT to be negative. Other than this, these are completely independent parameters of the defect, but these are the two parameters that will be related by the equation. Which I'm about to write down. No? Okay, any questions so far? Okay. So let me write down now the equation. I was hoping for the 4 blackboards of yesterday, so I could leave the equation on the blackboard. So I'm afraid you will see it and then I will erase it, but I can put it up again. So basically, this is simply a linear relation between these two things. Maybe before I write it down, no, I want to write it down. Where do I have it? Here it is, yeah. So the relation is that CD is some numerical coefficient that depends on P and D. Well, let's use maybe, depends on P and D, but doesn't depend on the defect, times AT. And this coefficient is some combination of gamma functions, P plus 2, gamma of P plus 1, over D by okay, now yeah, so this equation, this is the equation I was talking about. This equation was first encountered by Maldacena, Yukovic and Maldacena in precisely the study of radiation emission from an accelerating quark, 13. So it was in a very specific case, P equals 1, D equals 4, a line defect in 4-dimensional super young Mills. Then it was proven, yeah, it's only it's a consequence of supersymmetry, and it's true for all, I insist on this, all superconformal defects. Doesn't matter how much, yeah. As long as you have any supersymmetry, this is true. So it was then shown for all line defects with n equals 2 bulk supersymmetry, so in n equal to SCFT, less than n equal 2 doesn't have supersymmetric defects, so in a sense this is the general case of line defects in 4 dimensions, and this was shown by Lorenzo, Lemos, and Marcos Maineri in 18. Then the year after, Lorenzo and Magdalena Lemos extended this to surface defects in 4 dimensions, where now you can have them for n equal 1 supersymmetry. And in this paper, so that was the year after, and in this paper, they made a very impressive, in my mind, conjecture, namely they pulled out this formula with rather scattered data. Well, this was part of the data. Another part had to do with anomalies, basically, and I will, in a sense, if I come to it, talk about it in the holographic part. Still, you know, this somewhat scattered data, they just pulled out this formula. Now, we didn't know with Zhongwu about this, and we were thinking about holography. We realized that sigma mechanical is sigma gravitational if an equation like this holds. So we conjectured it. I sent it to Lorenzo. He said it looked different because it was other combinations. And it's probably the two are not correct for non-integer p, if I remember correctly, right? But then you checked numerically, and then Zhongwu showed that the two formulae were the same. And then, you know, we pulled forces together and proved it. Okay. Yeah, I mean, you need both of them. Of course, I should say also that for topological defects, both sides are 0, so it's sort of trivial. But for interfaces and point and local operators, one of the two is not defined. Yeah. Okay, so now, so this is the statement. Okay. Now, I would like to sketch let's see, yeah, you, no, I'm not sure it does, because the gamma functions seem to be fine if p equals to 0. Yeah. If I recall, I may be wrong, if I recall correctly, there were two different writings of this constant, and they only agreed for integer p and d, but had generic different analytical continuations outside. Okay, so that's part 1. Any more questions about this? You know, p is the number of dimensions of the defect, d is the space-time dimension. I'm assuming they are integer, but you can continue analytically to, you know, people do this. Yeah. Space-time is for now flat, yeah, absolutely. Yeah. Okay, now I said I will sketch the proof. Basically, in a sense, I could tell you, please look at the paper. The proof is very detailed there. But there's a main character that I want for the rest of the talk, which is the two-point function. It relies on the two-point function with one energy momentum tensor and one, let me put it upstairs, and one displacement operator. And this, I will tell you some things about this. Now, how much do I want to tell you about the proof? basically it has two strands. I would say very little about the proof, but it has two strands. The first strand is to classify all super conformal defects. Now this was done in part already by the UCLA people, so Eric Docker, Michael. They were coming from supergravity, but basically the technology is the same. John Estes, Daria Krim, and Paul Sorba. And then that's an old paper, right? Michael, forget from one. Then Agmon and Wang did a very detailed, in 2020, very detailed study of line defects. And independently, actually, Mike Duff had many of these results in his scan of superconformal brains. He hadn't published it, but he wrote it up later, so he sent it to us. But essentially, the key point is that superconformal algebras are extremely rigid, and therefore all you have to study is the embedding of superconformal algebras, okay, to make a long story short. And we did this in great detail, and there's a table, but I cannot show it to you, but you can find it in the paper, of all possible superconformal defects with more than two or more transverse directions, because that's what interests us. Remember, interfaces or boundaries are not part of this, and twisted potentially rotational invariance, because otherwise the things I'm talking about are not defined. They are more complicated. You know, here I assumed tensor structures that are consistent with the rotational invariance. We just have all cases. And not only we have all, so you give me a bulk superconformal algebra, I tell you what kind of defects it admits and what is the unbroken superalgebra. Yeah, exactly. And actually, it's more than this, because by scanning the literature, you can find all these cases in some form, either in supergravity or in conformal theory. So they all exist in a sense. Right. So if you are interested in this, look at the list in our paper. And now, roughly speaking, the way now you proceed, as I said, is by looking at this two-point function. Now, twisted, I mean that if you have, yeah, but only in codimension 2, you can have an unbroken SO2 that is a linear combination of rotations and R symmetry. Doesn't happen for higher codimension. Yeah. Okay, now let's think about this two-point function. So this is a bulk boundary two-point function. So if it were not for spin, it would depend on one parameter, but because of spin, there are different tensor structures, and this depends on three parameters. Now, this was analyzed in a very nice paper, very much used by Below et al. 16. And they called, so we used their notation, they called this B1, B2, B3. Now, I'm not going to write down the general form. It would take me too much of time, but I will write down one component of this, namely, if I have the energy momentum tensor with one transverse and one longitudinal index, could be time actually, with dj, then this has the so this is completely fixed by the unbroken symmetry, namely SO2P, the conformal group, times the rotations SOD minus P. Okay, so this completely fixed this two-point function, and it has some kinematic stuff, P minus V, X minus Y beta, alpha, X minus Y to the 2P plus 2. And then there is a Gij of X minus Y. And the Gij, I will write it here, is minus B3 delta Ij X transverse squared over X minus Y squared plus, so that's one tensor structure. Another one is Xi Xj. The rest is fixed by scaling symmetry. And the fourth one is again Xi Xj over X minus Y to the fourth. So this is this particular two-point function. So, sorry, let me put this down, dj. This is the point y, it's only a point on the defect. This is the point x. So x minus y is this. X minus y's transverse is simply x transverse. That's why I don't write the y here. And likewise xi xj and so forth. Okay. So now, you know, this correlator depends both on x minus y and the transverse distance to the defect. Absolutely. Yeah, x is outside the defect, y is on the defect. Yeah. No, it's a bulk to boundary two-point function. Now notice that the leading light consingularity, you know, when we set this thing in motion, this is the leading light consingularity, x minus y to the fourth, and this will play a role when we discuss radiating charges. Okay, this is, so up to here we only used unbroken SO2P times SODP, but as these people showed below, Loria, Maineri, and a fourth Italian, yes, Gonsalves, so a fourth non-Italian, exactly, as they showed, B1, B2, B3 are not independent parameters. Okay, this is a key point, and the reason is obvious. You see, you have two word identities. First of all, if you take T mu, D mu with a dk, this is morally related to dj decay, remember, because of the broken conservation law. And the second thing is that because the displacement is doing what it does, it displaces the defect, if I integrate the displacement uniformly and have anything else here, for instance, T mu mu, this is the same as taking a j derivative of T mu mu. So you see, schematically, TD is related to DD, and dt is related to the one-point function t. And by using these word identities, you can fix completely B1, B2, and B3 in terms of the one-point function of the energy momentum tensor and the two-point function of the displacement. No, B2 doesn't enter here. It only enters in the other components. So in this one, it's only B1, B3. Okay. Okay, so they derived they derived equations that relate these things one to the other. And now the key point is that the supersymmetry equation, I'm calling it BPS, it's really also a misnomer because it's not the usual kind of BPS, but let me call it the BPS equation, which I erased, becomes extremely simple. It's still there, yeah. Okay, good. So it becomes extremely simple in terms of these coefficients. 2D B1 is P plus 2 B3. And in a sense, so this is a rewriting of the BPS equation for this correlator, and this rang bells to us when we were thinking about the radiation problem. Okay, now I'm not going to go now through the rest of the proof. Basically, the proof goes along the lines of what Lorenzo had done in the special cases, namely, you consider the supermultiplets, both T mu nu, so I'll just say words, okay? But please look at the proof if you are interested in it. So basically, you consider the supermultiplets of T mu nu and of dj. Both are top components of their corresponding supermultiplets. So T mu nu is the top component. Then what appears here are the supercurrents, J mu, a spinor index, and they can have also an R symmetry index. Then you have the R symmetry currents. Again, I'm suppressing R symmetry indices and so on. And the dj is also the top component, and then it has basically the dual to the Golstino. Yeah, so what we did, we worked out those that weren't known. I forget to say that you need to only do this for the minimal supersymmetry allowed in any given dimension. And D and P, you take a pair D and P, you take the least allowed supersymmetry, and then the higher supersymmetries are automatically, So we considered indeed all the minimally supersymmetric defects, and Zhongwu worked out indeed the transformation laws. You have to use some technology that I think Trepagnier used, right? Where is Chris? In his thesis, or at least Nadav and Trepagnier in King's College used. And it's straightforward. You write down the generic allowed tensor structures, and then you require Jacobi closing, and that does it. So it takes work, and that's in a sense most of the work. Only those two. Actually, this is the hard one. I mean, this is pretty easy because it's a smaller subalgebra. This one is, you have to do it. And then the next thing, to unify the proofs, you have to make a nice choice of bases. The proof only depends on one supercharge. So remember, the supercharge has a spinor index, and that's an RP index, and it has a, how should I call it, an R symmetry index. So you can pick judiciously just one component and only look at the reduced supermultiplets of this component, and then, okay, then you work. Let me skip this because I won't have time to go through. But it only depends on one supercharge. That's why, as I said, then supersymmetry works. I mean, if anyone is interested, I can go through this in some more detail. So say again. So you need to use the I mean, basically what happens in words is that when this relation works, a particular component, namely the ZZ, where Z is a complex transverse coordinate component of this, gives you a correlator which is a double derivative with respect to Z. So you need to use the superalgebra in this particular basis to transform lower component correlators to derivatives of the higher. I mean, yeah, it's technical, but we can go through it if you want. Those that have any interest in this, we can go through it. Because I want to talk to you about the other two things. I mean, this is in a sense, we were happy with this, but it's all technical and there is no new ideas other than doing properly the whole. And all the profs work in the same way. That's nice. I mean, independent of the superalgebra, they all work in one go. No, no, it can go either way. Yeah. That's one of the ways in which it is an unusual equation. It's not a bound. Okay, so now I want to tell you a little bit about holography and brain tension, which, as I said, was in a sense motivated by our work with Shira. So that's part 3. Now, if there's anyone in the room that doesn't know much about holography, well, I think most of you do, but just I remind you that here is the story. We have a defect in flat space-time, and now we add, so this is the dimensions, and now we add the anti-de Sitter dimension, d plus 1, dual to SCFP d. And now the defect is p-dimensional, and to a first approximation, it is dual to some kind of brain, a p-brain, which hits the boundary. This is the boundary of ADS. It hits the boundary of ADS on the defect. So for instance, if you have a line defect, this is a string whose trajectory finishes on the line defect. Okay. So this is the picture, right? Now, however, this is only a picture because, as I will say in a minute, as soon as the brain is not classical and probe, you have to take into account the back reaction. Then it becomes supergravity solutions. Many of them were derived by Michael and friends. You lose the brain, you have some sort of fluxes and so on. So it's simply some smooth geometry here, and only on the boundary you recover a singular submanifold, which is the brain, the defect, I'm sorry. So, you know, in particular, if you think about the defect as a point operator, so it is the end point of a world line, of Euclidean world line in the bulk. You can draw this only if the point particle doesn't back react and become a black hole. If it becomes a black hole, you know, it's some thick object and so on and so forth. It doesn't matter for us, you know, it can be anything. We won't use this except to fix coefficients. Okay. So let's set the radius of ADS to 1, just to work in some unit.
I mean, I know it's not within the case of the study, but case of 4-dimension 1 defect, you can have rather simple back reaction.
Yeah, it's the only case where Israel matching allows you to do. Yeah, I'll say just a word about it. But in the other cases, it becomes, flat solutions. Okay, so let's think about precisely a massive particle. So now we have a massive particle in ADS, and as we all know very well, mass cannot be defined locally. Nothing can be defined locally in gravity. So the only way to define an invariant mass, differ invariant thing, is by going to the boundary, either asymptotically flat or asymptotically anti-de Sitter, and define invariant quantities in terms of boundary data. Okay, this is the generic mantra. And for a point particle, we actually know how to do this. The invariant mass or energy is the scaling dimension of the dual operator. If you want, it's the same as integrating on the boundary the dilatation charge, so it's something like this mu x nu, that's the dilatation charge, T mu nu. And now if you expand this out for a free particle that doesn't interact, and I'm using here 4 dimensions just to lighten the formulae, but the story is generic. We know the formulae by just looking at the wave function of the particle. And then if it interacts, it has GR corrections, and so on. Where M0 is the bare mass. If I consider a point particle with bare mass M0 before it's screened and renormalized, this is the M0 occurring here with some expression like this, which I can expand out. So it starts out as M0, and then, expand the square root, it has, say, 3 over 2 M0, in this case, plus 9, 8 M0 squared, plus dot, dot, dot. And if there are also GR corrections, I will also get corrections with coefficients here, G Newton M0 plus G Newton M0 squared plus dot, dot, dot. And note that in a sense what one is resumming here, this is the Schwarzschild radius in a sense of the particle. So here one is resumming gravitational back reaction. And this is 1 over M0 is the Compton wavelength of the particle. So here is one is resumming quantum corrections. So compared to the radius always of ADS. So, if the Compton wavelength is small, these go away. It's a classical particle. If the Schwarzschild radius is small, those go away. And you are left with M0. But a priori, the full expression is this. And it can have other terms because it can have also other interactions and so on. The famous ADM mass, or its analog in ADS, is basically resumming this. Okay, so the invariant ADM mass, it's classical, there are no quantum corrections, it's resumming this. But in CFT, we can do everything in one go, right? Just delta resums everything, that's the invariant energy, period. Yeah, that's simply dimensional analysis. But you can write down Witten diagrams I'm going to do. The radius is set to 1, yeah, the radius is set to 1. So in a sense, this is an expansion in lambda Compton in units of the radius, and this is an expansion in lambda Schwarzschild in units of the radius, okay. So this is the generic story, okay. And now the question, the obvious question is, okay, what if we have, as opposed to a point particle, a brane? Well, this ADM mass and its extension can be easily extended. And actually, even though it wasn't said like this, in the early 2000s, Myers, Oberson, Hallmark, I think Townsend also, and various people did effectively write down the extension of the ADM mass to ADM tension, and it boils down, I won't write it down explicitly, it boils down to using this formula here, but integrating over a sphere around the defect as opposed to a sphere around the point. The defect now is extended. You integrate the dilatation current around the sphere, and then you find a formula. So again, it wasn't written like this, but it's moral equivalent. You find the formula which is necessarily proportional to the 1-point function of T mu nu, so it has an AT, and then it has some numerical coefficient that depends on P and D. So this is the gravitational tension, and the name is well deserved because the 1-point function of T mu nu tells you the fall off of the metric in the dual picture, far from the defect, and that's exactly how you define gravitational mass, on how it affects the metric far from the defect. But then, we said, yeah, but there is another thing you can do. If you have a string, you can define a tension without gravity. What do? You just a violin string, you strike it here, you strike it there, you measure the 2-point function, and this gives you a different measure of tension. And so this is the C mechanical, but we also called it C inertial in this paper. And now this is obviously something that will be proportional to the norm of the displacement field, K. I don't have to do it. So it's CD times some other combination of P and D. And now the question is, how do you fix these numerical prefactors? And again, because time runs, let me tell you the story without writing the formula. It's a nice story, and it's something which I think is the beginning of an unfinished story, because what we did was to try to fix these coefficients by going to the limit of a classical, so no quantum corrections, probe, no back reaction, brane, and then demanding that both of these definitions, both sigma gravity and sigma mechanical or inertial, reduce to the bare tension which enters in the Nambu-Goto action of a probe brane. A probe brane doesn't thicken, it's if it's classical, it's basically completely controlled by the coefficient in the Nambu-Goto action, which is the tension, and therefore you just check this limit. Now, I must say that, in a sense, an analogous calculation is being done when you calculate Graham-Witten anomaly coefficients classically, namely as conformal anomalies of classical submanifolds. Morally, it's the same. Simply, this is more general because you don't need to be in a case where there is a conformal anomaly. For instance, line defects don't have that kind of conformal anomalies, and yet you can do this like that. Now this, again, I'm going to skip the formulae because it cannot be done on a blackboard. Sounds simple, but actually it's really a headache. The reason is that you need to calculate the dual fields to T mu nu, well, T mu nu, that's the graviton, and to dj, and dj should be somehow a transverse coordinate of the brane. right? So naively, you would say, okay, what's the big deal? Let's do it as follows. Anti-de Sitter in the vacuum has a metric in Poincaré coordinates, which is dy m, dy n, eta mn over y naught squared. That's anti-de Sitter. The brane, since I am sitting in the conformally invariant configuration, is an anti-de Sitter submanifold of this, which sits at yj, so yp plus 1 up to yd equals to 0. That's the ADS submanifold, as you saw in Shira's talk. And therefore, this is the perturbation of the metric. If I write now the metric as G mu nu is this metric, let's call it G bar mu nu plus H mu nu, I need to calculate correlation functions of this, which is dual to T mu nu. And what about this? Well, this has some embedding coordinates. Let's call them yj of the longitudinal ones, y alpha. And this should be dual to the displacement. Well, that's wrong, actually. If you do this, you get nonsense. This is not the good field for the displacement. It was already noticed, I think, by Sept and collaborators, that for defect fields, you have to go to another set of coordinates where the conformal symmetry only acts on the longitudinal coordinates. So there is another set of coordinates which looks like dx mu, dx mu, dx alpha, dx beta, eta alpha beta over x0 squared, and then dxi, dxj, and here you have functions of the transverse x. So it's a rewriting, it's not just a change of coordinates, but it is in this coordinate system where the transverse x seems to be the dual to the displacement operator. Okay, that's easy. The problem is, how do you normalize these things? Remember, normalizations were everything in this calculation, and the word identities depended very much on normalization. And when you calculate one-point functions of the graviton, you want to do it in the Poincaré coordinates. And when you calculate displacement operators, you want to do it in these coordinates. So we found a cheap solution to the order that we worked. And then beyond that, it doesn't work, which is to check the conformal word identity explicitly. So we calculated, again, this T mu nu dj, and we checked that the coefficients are exactly what they should be. If you just take the displacement to be xj, no further corrections, and the graviton, the T mu nu to be h mu nu in Poincaré. So at this order it works. Beyond, the change of coordinates is non-linear and field dependent, so it's not clear how you put cutoffs and so on. And I think, I mean, Michael has come to this problem, I think, differently, but it's a very important open problem. I think we don't know how to really consistently compute bulk defect correlators in holography in general. If you look at the whole literature, it's all defect correlators, all bulk, but the mixed ones are absent. Anyway, so we did this. We fixed the coefficients that I showed here, where we fixed the coefficients gamma, and by fixing these coefficients, you can show that the BPS equation is sigma gravitational and is sigma mechanical. So if nothing else, this is a much nicer form of this equation, and it is unusual. Yeah, it's a similar thing.
Somehow, get by and get this type of defect, bulk defect correlates.
I think it's all leading order, indeed. I mean, what we did also in terms of Witten diagrams, it's leading order. So you have here the defect in ADS. It can emit a graviton. It can emit a displacement. But there are no loops, and then at this leading order it seems to work. At the next order already you just have a problem of how do you cut off here as opposed to here the space, because it's a field dependent change of coordinates, so it's a mess. I mean, maybe there is some smart way, we don't know. Well, I would be, let's talk about it. I mean, I would be very interested to know about this. As I said, the only thing we did was to check the conformal word identity, and then we said, okay, so we are okay. But this was simply in the calculation of these coefficients, okay. Anyway, so this is the BPS equation, and it is unusual, you see, because it does not relate tension to charge. It relates to tensions. There is no bound. In an example that I may not have time to show to you, it can go both ways. And I don't know what it is, but of course it rings the obvious bells. Could it be that M theory somehow in the deep UV wants this for brains, which is the extension of gravitational equals to inertial mass, the principle of equivalence. But these are fantasies. I don't know if there is anything concrete one can say. Anyway, it's a very peculiar equation. Now, I ran out of time. Do you want me to say a little bit the fourth? Yeah, okay. Let me show you this because it can be done while talking about number 4 also, which I want to tell you just a little about, because this I think is also, this is a problem, a century-old problem, goes back to Abraham, Dirac, Lorentz with a T and so on. It's the question of whether you can write down a radiation reaction equation for a charge. There's no reason why it should be possible. So I'll say this and then show you the example. So you have a charge. So you have a charge which undergoes some motion, including accelerating motion. And since it radiates, there is friction, so you can write down a friction term. And there is a force, the Abraham-Dirac-Lorentz force. This force includes a term called the shot term. It's a derivative of the acceleration. And despite many very smart people trying to derive this in QED, they haven't succeeded. And the reason has to do with the fact that you have to separate self-energy of the charge. The charge has fields. When it moves, the fields are dragged along. There is some self-energy from radiated energy, okay. And the self-energy is singular, of course, if you have a Coulomb charge, the self-energy diverges. So is there any possibility that this may still be a consistent low energy effective action? What I mean by this is that I have S Maxwell plus a point particle, which is charged. And I want to write down a consistent equation for the motion of this particle. So I think the nicest post-war paper was a paper by Teitelboim, which is very precise in setting up the problem, in giving some sort of proposal for what to do, but then doesn't do it. And then people later kept trying, so Galchev and various people have written papers. You may say, well, is it important? I'm not sure it's important, because in QED you don't need this, you don't need a heavy external probe. But people doing lasers and so on seem to think it's important. I have no idea. In any case, I can make one comment about this, and also at the same time show the example that Matt asked for. So let me tell you what the statement is, basically. There is a very simple case where you can study the problem. This is n equal 2 Maxwell theory in 4 dimensions, if I can find it. By the way, this is how the whole story started, okay, in the Maldacena-Ljukovic paper. So I don't know, to decide what to tell you, how many minutes do I have? Oh, and these, I'm sorry. Okay, that's plenty, yeah. Okay, so then let me tell you about the Maldacena paper. So he said, well, we can calculate Maldacena-Ljukovic and Maldacena-Correa-Hen, and the fourth author before, and also papers by Fjoll. So there's a famous, formula for radiation. You find it in Jackson, for radiation from a moving charge. The radiated energy is the integral of the square of the acceleration. And there is a coefficient here, which nowadays you write as 2 pi b. And this is called the Bremsstrahlung function. I always forget how many S's I have to put. It's only 2, and it's this thing. Okay. So for QED, this is simply 2e squared over 2q squared over 3. Okay. Now, you can compute this using conformal field theory. So, of course, if you look at Jackson, it's equivalent. But nowadays, you could do it as follows. First of all, by tilting the word line, for instance, you can put an oscillatory motion of the word line of the charge, calculate this diagram, and cut for the imaginary part, which gives you the emission. And this gives an answer, which is B equals to 1 over 12. Obviously, it depends on the displacement norm, because it's a 2-point function of displacement. And for D equals 4, P equals to 1, line defects, it is 1/12 CD. But you can do something else, which is to say, well, let's consider a circular line defect in Euclidean. If you go to Lorentzian, it becomes a quark-anti-quark accelerating uniformly for all times. And now you can measure the emitted energy at an appropriate place. For instance, here, this gives you an answer which is proportional to T++. And this is conformal to a straight line defect. So you can calculate this using conformal transformations. And obviously, you get an answer, let's call it B prime, which is now proportional to AT, because it's the 1-point function of the energy momentum tensor. And now, what they noticed is that the two calculations disagree. And they said, well, the difficulty is in separating radiation from self-energy. And they found a way to fix it for n equal 4 super Young-Mills, which is the following. They said, let's change the energy momentum tensor. It used to be T mu nu, but now we can add something proportional to eta mu nu box minus d mu d nu times a scalar whose dimension is 2 less than t mu nu, because I also have two derivatives. There is such a scalar in the supermultiplet of t mu nu of n equal 4 super Young-Mills, so you can use this one, and then they said if you fix psi so as to remove the singularity of the one-point function as the defect, then the tilde b prime is equal to b. And this works indeed. It's a wrong logic giving a right result. That's what smart people do. You go through a wrong path, but the answer is right. That's an improvement, yeah. So you'll say, yeah, I'll tell you now. This is the traceless guy. This one is conserved, but not traceless. Okay. It's a deterioration, yeah. But it is like improvement term, yeah. It's not traceless anymore, but it's always conserved, and you are free to decide that that's how you should measure energy. It's a conserved energy momentum tensor. Now here is the case which shows this very explicitly. So n equal 4 super Young-Mills, n equal to Maxwell. That's the simplest one. It's all free and you can compute explicitly. Right. So n equals to Maxwell, I have the gauge field and two scalars. I have the line defect, let me write it here, which couples to the gauge field and to the scalar. A priori, the two couplings can be different. That's a unit vector. Well, let's call it phi1. Right, and this is half BPS if E is equal to G. Okay, now here, it's straightforward to compute everything. So T mu nu, I don't have to write it down. It has the improvement term 1/6 eta mu nu box minus d mu of phi squared. And the rest is the known things. And dj is the electric field plus g times the derivative of phi. Phi is phi1. This phi squared, okay. Let's call it. So I pick one of the phi's, okay, phi and phi. Okay, so now when you put such a defect in the problem, you can calculate all the things I told you about there. Since all you need are the classical backgrounds, and you find, first of all, AT and CD, it's very simple, and they obey the equation, which is in this case minus 18 AT is CD, if and only if E equals to G, that's normal. But what I want to show you is the following thing. What happens now if you do the trick of Lukovich and Maldacena? So by the way, in this problem, that's the BPS equation, and it is obeyed if E equals to G, yeah. I mean, if you put P equals 1, D equals 4, you will get minus 18 in my formula, yeah. Okay, now let's play the trick of Dasena, T mu nu, and Lukovic. I'm going to add psi eta mu nu box minus d mu phi squared. And now I'm going to fix psi so as to remove, by the way, yeah, if E different than G, it can go both ways. Okay, so that's the example that there's no bound. So fix psi so as to remove the singular stress, namely Tij of x, remember, which was, I forget now the thing, but it had a delta ij over x transverse to the d, and it had an xi xj over x transverse to the d plus 2, and a coefficient. So you can fix psi so as to kill this. So now there's no singular stress in this improved or disimproved energy momentum tensor. If you do this, you don't get agreement between the two calculations of radiation in general. So in general, the Bremsstrahlung function is different from B. Actually, it so turns out that for Maxwell theory, the two calculations agree without improvement, even though the energy momentum tensor is singular. So what I'm trying to say is that removing the singularity is not the medication for making the two things agree. But if there is supersymmetry, and you calculate the psi that you need, which in general depends on the ratio E over G, so when this is 1, this is precisely minus 1 over 6. So this, in the supersymmetric case, the improvement removes the improvement of the energy momentum tensor. And this is very nice because the improved energy momentum tensor, this guy, violates the null energy condition. You see, d plus of phi squared has no sign, so it can be anything. So when we improve the energy momentum tensor of a conformal scalar, we violate NEC. Now what I'm saying is that if you redefine the energy momentum tensor without the improvement, and you have supersymmetry, then you remove the singularity and the stress, and you remove the NEC violation in the energy momentum tensor. And this is a general statement, so we could prove it for all defects. I'll write it here. The same modification, improvement of T mu nu that restores NEC also removes the singular stress of the static defect. Now, the reason we could do this is because in conformal theory you can easily weak rotate by weak rotating time. In a general QFT, this would be a total mess, but in CFT you can actually do this again. Please look if you're interested in the paper. So basically the same arguments here go through for any CFT. You kill this leading light consingularity, which violates NEC, and the same subtraction removes the singularity in the one-point function of Tij. So this is only true for supersymmetry. So somehow the hope is what? No, the hope, and then I stop, is that you see, if you don't remove the stress, you have a point charge, it has singular stress, and it has singular energy. The singular energy you can renormalize by subtracting the mass. That's part of your original effective action. It has a mass term, but there's no way you can remove the stress. There's nothing in your Nambu-Goto action to remove transverse stress, right? So somehow the whole thing looks from start inconsistent because you are trying to write down an effective action, renormalize the mass of the heavy particle, but you do nothing about the stress, and when you accelerate the charge, the stress also accelerates, is dragged along, and maybe that's the root of the problem. I don't know, but anyway, it's worth revisiting this problem with supersymmetric defects, where at least at this stage, it seems reasonable to absorb all singularities in the mass of the particle. And then the litmus test is, can you now compute the short term, which I don't know how to do. I mean, the honest thing would be to calculate, unfortunately, T mu nu dj decay, which is much harder. And this we don't know how to do. Yeah, I'm happy to discuss after the talk. Yes. So you can improve to remove the neck violation, or you can improve to remove the singular stress, but you cannot do both with the same improvement. For SUSY, you do both with the same improvement. That's the statement. There's not much you can add because it has to have the correct dimension. What is it? I mean, what do you have in mind? It has to be conserved, have the correct scaling dimension. Yeah, or in anything. Oh, you mean have other scalars, so play with more scalars? Yeah, I guess you could play with more scalars, yeah. But you see, the neck is there because of the improvement of the scalar energy momentum tensor. So in a sense, to remove neck, you have to remove all the improvements. So this gives you many conditions. Now it would be very lucky if somehow this is exactly also removing the stresses which come from each scalar gives a different stress, right? dj phi, dk phi.
Also, in full interacting theory, having a protective scalar is not useful, right? For extended. No, yeah. No, I'm talking about non-supersymmetric. Yeah, that's.
It's a little bit like an anomaly. You don't have SUSY, you can't find a scheme where you preserve.
I don't know, maybe. I mean, why anomaly? How do you see?
You can't find a regularization scheme that preserves.
Uh-huh. I mean, as you know well, indeed, this equation does relate anomaly coefficients, right? The extrinsic curvature square with the Weil tensor. When the defect has anomalies, yeah. But for line defects, for instance, there is no anomaly, so... yes. Yeah, then you need higher point functions, right? I mean, if you perturb a lot, you need higher orders. You see, just one dj is nice because it doesn't have cross ratios, so it's all fixed by data. Once you put two dj's, you need the theory, and you have non-trivial functions of cross ratios.
Geometrically, I don't see at which point I should use two
Yeah, you see, for instance, if you want to calculate this famous formula of emission here, Bremsstrahlung formula, it's proportional to acceleration square. So a priori you need two displacements to compute it. Now, because this is very universal, probably it doesn't require the full correlator. But,
Said that a major open problem in holography for defects is the holographic renormalization of
yeah.
displacement operator. It's a well-posed problem, I think, but it's just tedious and boring to do.
Oh, is it well posed? Yeah, I don't know that it's well posed, is it?
There are issues about the defect.
No, but you have no good Pfefferman-Graham coordinates, right? You have different ones for bulk and for defect. So how do you do that?
Holographic renormalization with any coordinates like
Mhm.
So in top-down examples, people computed this correlator cycle paper you were saying.
Yeah, but it was leading order. I mean, if you go beyond, then the cutoffs, for instance, the displacement operator cuts off x0 in the calculation. The other one cuts off y0. The relation between x0 and y0 is a mess. It includes the transverse x and so on. So I don't even know how to do this. You mean translate xj to yj? But no, you cannot do this because then you have the problem with the graviton. You know, the graviton, I mean, it's always, maybe you guys have some idea, but it's always, if you want, the problem is, for instance, that x0 and y0 are related here with some function of xj. So, you know, usually in holography, so if I do bulk things, I put a cutoff on this equal to epsilon. If I do defect things, I put a cutoff on this. And then I renormalize. Now here, you know, to leading order, we could put the same cutoff. But to higher orders, I don't know how to do it. Sorry. I know it, yeah, it's a very explicit function, you know, it's something like 1 minus 1/4 x transverse square over whatever. Yeah, you have it. But x transverse now is going to be the coordinate of the brain, right? So in a sense, it becomes a field. So how do I put the cutoff? You know, if I do the two-point function of dj, then indeed I find that in these coordinates it's a massive field with mass giving p+1 as scaling dimension, and I do essentially the usual stuff by a cutoff epsilon. If I do gravity, I put this. But what do you do for a mixed correlator? And do you cut them off differently, or? I know that, Michael, you tried this, right, in supergravity, but I don't know, did you conclude anything? Yeah.
Take that discussion offline.
Okay, yeah.
And Costas.
Thank you. Thank you.